You're going to videos?
Video both. Okay, here's 31. Helicopter. Look at that helicopter.
So better than mine.
And the helicopter's lifting a car. I'm taking a lot of time on this car too.
That car is way bigger than the helicopter.
Okay, and we get an acceleration of this thing upward. And it is what? 0.6? Get out of there. 0.6 meters per second squared. And we know the mass of both. Question A is what's the lift force on the rotors? Here's the simple way to deal with this. Just pretend that these two things are like one object inside a box. And who cares even what's in the box? There's rotors on top of the box propelling it upward. We want to know how much force is on those rotors to produce this 0.6 acceleration. Okay, so I just take the combined mass of these two, which is, what, 77? Is that right? And say, okay, what has to happen to produce an acceleration upward? So I go force diagram here. So I've got a weight down, and I've got a force up, the air pushing on the rotors. That force upward has to be larger because it's accelerating upward. So one way to say this is that the net force would be whatever the upward force from the rotors is minus the weight. And since acceleration is force over mass, if I rearrange it, force would be mass times acceleration. So I could just write equals mass times acceleration here. I know the total mass, I know the total acceleration. The weight I can figure out, it's going to be 77,000 newtons. Because remember, the strength of Earth's gravity is 10 newtons for every kilogram. That's the strength of the gravitational field. So times that number by 10. We've got the weight, which means then if I just rearrange this, it's ma plus w. I know some people don't like plugging everything in at the end. Probably most of you like to plug the numbers in as soon as you know them. I used to be that way too. But it's easier to write if you don't. So we get 7,700 kilograms times 0.6. And then I'm adding in the weight here, which is 77,000.
Wait, shouldn't it be negative though, since you're going up and since that's pulling them down?
No, because it was negative on the other side, but I'm rearranging the equation to solve for f. So does someone have an answer on this that did it like that?
Well, the 7,700 times 26 is 4,620.
Yeah, it's over on the bookshelf. Okay, say that number again.
4,620. Wait, that was in newtons though. Never mind.
That's what it needs to be in. So we're going to end up with a force on the rotors of, what is this, 81, 82?
81.
8120? That's not right.
AP Physics.
Yes, it is. 81,620. Now, some of you might say, I don't like that at all. So let me work it out a way that's a little bit more conceptual, maybe, and see if some of you like that version better. So what we know here is that if the helicopter is just hovering with the car, then that would mean that the force up would be more like this, and that this guy now would be balanced to that guy, right? Because then there would be no acceleration. The forces would be balanced. Since there is an acceleration, the acceleration is caused by this extra amount up here, which we can call the net force. So I could just say, well, what is the net force based on what I know? Well, put in 0.6 for this, put in 700 kilograms for this, and the net force, which we already figured out, would be 46,200 newtons. So then you just have to say, well, the total force here on the rotors is the weight plus the extra that makes it accelerate upward. So the weight was 77,000, add in this amount right there, and you get the exact same number that we got before. So you don't really have to set it up like all equation-y. You can just kind of think through it on most of these if you draw your picture well. Questions on that?
Isn't there a part B?
Part B? Oh, you're right. Part B, we're just getting to that, is what then is the lift force on, or what's the tension in the cable? Okay, now if you're dealing with a tension in the cable, you're forced to think about what's inside the box. So now I'm just saying, you know what, I don't really care what's lifting the cable up. I don't care about the helicopter at all.
So then can you put the propeller on the cable?
Sure, if you like.
Yes, angry pigs.
Now there's a tension on the cable upward. There's a weight on just the car, which is 1,200 kilograms times 10, so 12,000 newtons is the weight. And I know the acceleration for the car is exactly the same as it was for the black box moving upward, the helicopter plus the car together. So I really can use the same trick I just used, which is I could say, well, if they're just hovering, then those are the same, 12,000. In this case, I'm going to need some extra. And the extra is going to be the net force. And the net force in this case is the mass of the car, 1,200, times by the acceleration that is the same for the car, 0.6. And what is that number? 0.6 times 1,200? Calculator people? Fine, you make me do all the work, don't you? $720. So the extra is 720 newtons, which means that you take the 12,000 weight, add in 720, and this whole side here must be 12,720 newtons. Is there a part C, or are we good?
It goes all the way part
What was
C.
your final answer?
12,720.
Okay.
Does that agree with the book? Okay.